Hello, everybody. Welcome to the second session of the second season of the Isogeny Club. Today we have almost Dr. Andrea Basso, because he just handed in his PhD thesis at the University of Birmingham and is awaiting getting the PhD. But he's also already started at the University of Bristol as a postdoc. And today he's talking to us about a post-quantum Oblivious PRF from Isogenies. So Andrea, the floor is yours.
Hi, everyone. Thank you for being here. Yes, today I would like to talk about my project on building a OPRF or Oblivious pseudorandom function from Isogenies. As a bit of context, this has been a long-running project. 2 years ago now, I was part of a project that cryptanalyzed an existing construction of an OPRF based on Isogenies, and we proposed an attack against that. And since then, I've been trying to fix it and trying to get some kind of better OPRF from it. And it's been mostly a struggle until I finally managed to get some kind of solution last year. That was just a couple of months before the SIDH attacks appeared. So at that point, I almost gave up on it. But then thanks to the SIDH countermeasures, it somewhat came back. But we'll see that in time. So first of all, what is an OPRF? An OPRF is a two-party protocol between a client and a server. Together, they want to jointly evaluate a pseudorandom function on an input chosen by the client and with a long-term static key held by the server. So what you see here is sort of the usual setup with a two-round protocol. The client sends a message that is based on the input M. This double brackets is to denote that the message itself is hidden, but it's dependent on it. And the server simply responds with some kind of function based on the input they received and its secret key. And this should be enough information for the client to compute the output of the PRF. And the PRF is a function, so it needs to be deterministic on the input M and the function K. And one of the key properties of pseudorandom function is that it's unpredictable. So we want that the client, when it evaluates the function on an input M, learns the output on that specific input and nothing else. So the client should not be able to evaluate the pseudorandom function on another input, unless they interact again with the server. And at the same time, this is an oblivious PRF. So we want that the whole transaction is completely oblivious and the server learns absolutely nothing. And this must hold in the strongest sense possible. So the server should not learn the message M, the input M, but should not even learn a hash of it. Or even if the possible messages are only two, the server should not be able to distinguish which one of the two messages are used. Now, this may seem somewhat of an abstract construction. Why would we need this? Surprisingly, an OPRF has a lot of applications. I forgot. We also have some OPRFs have also one additional property that is called verifiability. In that case, if an OPRF is verifiable, the server first starts by committing to its secret key K, and then during each execution, he also reveals a zero-knowledge proof pi that its computations were honest and that he used exactly the same key that he was previously committed. This helps. This guarantees that everything was honest and that if the client interacts multiple times with the server, the same key is used across every execution. As I was saying before, this is a surprisingly useful construct that has many applications. And for instance, some of them are very practical. The Microsoft browser Edge uses an OPRF to check that the password that you stored in the browser have been leaked or not, without ever revealing the password to any external source. They're also used in Opaque, which is a password authenticated key exchange that allows a client and a server to authenticate each other when they both know the same password without the need for the password to ever be communicated explicitly. They're also used in Privacy Pass, which is a protocol developed by Cloudflare to get privacy-preserving CAPTCHAs. But it has also many applications on the more theoretical side, such as in private set intersection, adaptive oblivious transfer, and so on. And just to sort of give an intuition of how these OPRFs are used, they are often used as a sort of like secure brute force resistant version of hash functions. In many protocols, we need to derive some sort of randomness from an input, and this usually happens deterministically. So in most cases, we just use a hash function, we hash whatever our input, and we get something random out of it. However, this doesn't really work that well when the input doesn't have that much entropy. If you're hashing, say, phone numbers or like passwords, they might be very short. So even if I give you the hash of a phone number, you might be able to obtain the phone number itself by simply iterating over all possible phone numbers. So OPRFs can be a solution in that case, because in order to evaluate the pseudorandom function on a message, it requires that the client interacts with the server. So as long as the server does not allow too many interactions, this prevents any sort of brute force attack. And at the same time, we need this to be oblivious so that we have no leakage and this value that we are hashing doesn't get revealed to the server. To give you a sense of how OPRF work, we can look at HashDH, which is possibly the most simple OPRF based on diffie elements. So this is a classical protocol. Say the client has an input M. What they do is simply they hash it. So they map it to random group element, and then they raise this to a random value B, where B is sort of like a blinding value. This is then sent to the server. The server receives the input and responds with that raised to its public key K. Now, since the client knows the blinding value B, it can simply undo this to obtain the output hash of M raised to the power of K. And again, the server doesn't learn anything. And this satisfies all the properties of an OPRF, because we have that the server doesn't learn anything. Since we raised this input to the power of B, B is uniformly random, so the group element that is sent to the server is also uniformly random. At the same time, the output is deterministic, because it only depends on M and K, and it's completely independent on the blinding value B. And the client only learns one output. Since we are hashing the message M to a group element, the client cannot easily compute the discrete log. So given this information, the client cannot just transform this into hash of M prime for a different M prime to the K. So this sort of is an overview of how OPRFs work and an example of one. Is there any questions so far on how OPRFs work, or specifically on HashDH? Okay, then I'm going to go ahead. Now, this is a protocol in the classical world, and it's very efficient. If we try to imitate this in the post-quantum world, things are not so easy. In particular, we face issues because, one, the server is holding a long-term static key, which in general is something that post-quantum protocols don't handle too well. Isogeny-based protocols have somewhat of an edge there and can do that better, but we are still struggling because to replicate this type of protocol in the isogeny setting, because here we need to hash the message onto a random group element to guarantee that the pseudorandomness of the OPRF. And as you probably know already, we don't have an efficient way to hash onto a supersingular curve, which prevent a simple translation of this protocol to the isogeny setting. So if we want to build a post-quantum OPRF, what are our options? The simplest way to do this is if we use some generic multi-party computation-based technique. We have multi-party computation that is post-quantum based on post-quantum oblivious transfer, and we can use that to build an OPRF. We simply select a PRF function, possibly an MPC-friendly one, and then we use MPC techniques to evaluate it between the two parties. However, there is a catch. All these kind of techniques require several runs of interactions. I believe there is some kind of impossibility result on fewer than 5 rounds of interactions for MPC with malicious attackers, and they're generally not that efficient. So, for instance, in the classical setting, the Diffie-Hellman construction that we've just seen is a lot more performant than the generic MPC-based techniques. So what we're hoping is that we can sort of do the same in the post-quantum world and get an OPRF that is post-quantum and is also significantly more efficient than what can be obtained by generic techniques. The first such proposal was an OPRF based on lattices that was verifiable, and it had all the sort of properties. It was verifiable and it was round optimal. So in that sense, it showed a clear benefit over generic constructions, but this construction can be characterized as a feasibility result, because each OPRF execution required the client and the server to communicate more than hundreds of gigabytes, which is clearly not practical. A second verifiable OPRF was proposed by Boneh, Kogan, and Wu based on SIDH. And this is highly interactive. It requires 6 rounds of communications, which already makes its advantage over MPC-based construction somewhat dubious. But it was also later broken by an attack on pseudorandomness. That's the one I mentioned at the very beginning. And more recently, it was broken by the SIDH attacks. In the same paper, the authors also proposed a second OPRF based on C-side that has a very different structure than the sort of Diffie-Hellman based one. This is unfortunately not verifiable, and it has 3 rounds of communication because it uses an oblivious transfer as a subroutine. So while this is as fewer rounds than a generic MPC-based one, is still not round optimal. And of course, also being based on C-side, there is always the question of C-side parameters, which one are the most, which one give the best trade-off between security and efficiency. And if we need to go for the largest parameters, its efficiency is quite limited. In this work, we focus on the verifiable OPRF based on SIDH by Boneh, Kogan, and Wu, and we basically address its 3 main shortcomings. We show an efficient countermeasure against the attack on its pseudorandomness. We show how to integrate the SIDH countermeasures to protect against the SIDH attacks, and we show how to make this round optimal. So let's see how the OPRF construction by Boneh, Kogan, and Wu looks like. The main idea is that if this is an SIDH square, we can take the share curve as the output of the OPRF, where of the PRF, the pseudorandom function, where the message determines one side of the square and this long-term secret key K determines the other side of the square. Now, first of all, as we said, we want this to be pseudorandom so that the client only learns one output per input. So we cannot have the server reveal its public key, because otherwise this would not enable the client to evaluate it on any message of their choice. So we can sort of ignore that part of the square and just look at this part. But now, while this would be secure from the server side point of view, this is not oblivious because the server sees the curve EAM, which depends on the message. So what we do instead, we skip this part and we have the client compute a second isogeny, a blinding isogeny that leads to another curve, let's call it EMX. The server can then compute the isogeny based on its secret key, K, in such a way that this isogeny is parallel to the isogeny that we would have had here or here, and reveals the final curve to the client together with some torsion information. And this torsion information allows the client to undo the blinding isogeny and obtain the curve EMK, which is precisely the curve that would have been obtained in the SIDH exchange. The main concept of this construction, it replicates the HashDH construction pretty closely. We map to the message to a group element, then we exponentiate, and then undo the other exponentiation. The way that they managed to get away without having a hash function was by noting that in SIDH we have torsion point images. So the main idea there is that when the server reveals this curve, provides just enough torsion information to undo the blinding isogeny, but not enough information to undo the second isogeny. And this makes the OPRF secure, or at least it was supposed to. Now, since this is all based on SIDH, we know that SIDH is vulnerable to adaptive attacks because this secret key is static and long-term. So to prevent against that, we have that the client also provides a proof of isogeny knowledge that guarantees that they know this isogeny here and that the torsion points revealed here are honestly computed. If we also want to get verifiability, we have that the server needs to provide a proof of isogeny knowledge that show that his computations were honest, but also we want the server to commit to its secret key by computing a parallel isogeny starting from a fixed curve E, provide a proof of isogeny knowledge that that was honest, and provide a third proof, that a proof of parallel isogeny, they show that these two isogenies used exactly the same secret. And it is precisely because we need these four proofs that the construction is still somewhat compact, but still like much larger than the Diffie-Hellman construction and quite a lot less efficient. So once we do all of this, we have that the output of the PRF is simply a hash of the input message M, the J invariant of the final curve, and the commitment curve. Now that we've seen how we can construct, or how Boneh, Kogan, and Wu constructed their OPRF, I can show you how the protocol can be attacked. This was part of joint work together with Peter Kushas, Simon Mertz, Christophe Petit, and Antonio Sanso. And the main idea there is that we break pseudorandomness, which means that we manage to get enough information so that after a certain number of interactions, a malicious client can evaluate the PRF on any input that they want. This is exactly the same construction that we just seen in the previous slide, just without all the proofs. From a pseudorandomness point of view, we can sort of ignore the blinding and unblinding procedure, and we just replace it with an oracle that, given an input M, provides us with a final curve. What we noticed is that if we query with a curve that lies on this green isogeny up here, and it's say like one step shorter, what we get is exactly a curve that lies on the green isogenies down there and is one step shorter. So if we repeat this process several times, we obtain all the curves between EK and EMK, which reveals the isogeny at the bottom. And if we have the isogeny, we also can obtain a kernel generator of this. This is sort of the first part of the attack. Then we repeat this 3 times with 3 messages that are linearly independent. If we do this, then we get these 3 kernel generators that we can combine to obtain a basis on EK, which is precisely an SIDH public key. Once we have that, we are in the SIDH setting. So given this, we can evaluate this isogeny at the bottom for any message M, which corresponds to evaluate the PRF on any message of our choice. As you may have noticed, the attack depends critically on querying with points of different order or using message isogenies of different degrees. And in the protocol, the client also provides a proof of isogeny knowledge, which reveals the degree of the isogeny. So the server can actually check the degree of the incoming message isogenies and sort of can demand that they're all of the right degree. In that case, it's still possible to adapt the attack only using full order queries, but we get an attack that is sub-exponential. This is not as efficient as the polynomial attack shown here, but it's still like very practical. Now that we've seen the attack, how do we prevent it? In general, it seems somewhat hard to prevent an attacker from doing that kind of operation and recovering a basis on EK. Here are three approaches that I considered. One approach is that we simply validate more. The attack, in order to work, required to use these very specific queries, very specific points. And this sort of goes against the protocol, because the protocol requires that these input isogenies are obtained by hashing a message. So we could simply validate more. But this is hard because the protocol is oblivious. So the only way to do this would be if the client provided a zero knowledge proof that they know a message, such that if you take the hash of it and you use that as a kernel generator, you get an isogeny of which they know the output. And this seems extremely complicated, and there is probably no easy way to do this without using very costly generic techniques. A second approach is more focused on the server. The attack is possible because the curve EK is always the same. So in some sense, if we could use some sort of dynamic values that changes every time, this would prevent the server, this would prevent the attack. But the issue there is that the protocol is deterministic. We want the output to be dependent only on the message M and the key K. And the message M is unknown to the server. So necessarily the curve EK must only depend on K, which makes it very hard to be somewhat dynamic. And lastly, we could just simply scale the parameters, right? The attack is sub-exponential. So that means that if we pick sufficiently large parameters, then the cost of the attack is higher than the security level. But that would require using huge primes. It would require using a prime of at least 16,000 bits. And this is before we even consider the SIDH attacks. If we want to throw in the SIDH countermeasures together with the larger parameters to prevent this attack, it would require using a prime that is almost 30,000 bit long. So how do we do this? How do we prevent this? The answer is that we don't, basically. We accept that the attacker will recover a basis on EK, that there is no easy way to prevent that, but we change the protocol in such a way that that basis becomes not enough for the attacker to evaluate the PRF. How does that look? So this is the original construction by Boneh, Kogan, and Wu, right? We start from the curve E0, compute an isogeny by hashing a message M and then using it as an SIDH to determine a kernel. And then the attacker recovers points P prime and Q prime and EK, and this allows to evaluate on any message. What we do is somewhat of a very minor modification, but that also has very profound implications. We start exactly in the same way, and we hash for a message that determines the kernel. But then once we arrive at the curve EM1, we don't stop there. We generate two new points that as a canonical base, and we repeat the process. We compute a second isogeny. And we want that each of these two isogenies is easily computable, so they must be defined, their kernel must be defined over FP squared, but we want that their composition is not. So their composition is irrational. Their kernel is not defined over FP squared, and actually the kernel of the big composition is defined over an extension field that is exponentially large. So what happens now is that when the attacker recovers the basis P prime Q prime, the basis that is defined over FP squared or over a small extension field has only the order corresponding to this isogeny. So this means that the attacker can evaluate the first part of the isogeny they need to compute, but they have no way to compute the second part of the isogeny. And to do that, they would either need to work with torsion basis that has exponentially many coordinates, or they would need to somewhat map the canonical basis from this curve down to this curve, but they don't know the secret isogeny phi k. So this successfully prevent the pseudorandomness attack, and as we going to see later, has also the added benefit that because these isogenies the full length of the isogeny doesn't need to be defined over fp squared. We can actually use smaller parameters, and which also lead, besides being secure, this also leads to a more efficient construction. Now that we've seen how to protect from one attack, we turn our attention to the next. How do we prevent the SIDH attacks? A first attempt was based on exploiting the specifics of the OPRF construction. We know that SIDH attacks require a torsion information of order n to recover an isogeny of degree roughly n squared. And in the OPRF construction, we have something like this, right? We have a message isogeny, then a blinding isogeny, the server isogeny, and the unblinding part. So if we take sufficiently long isogenies, where the isogeny is much longer than the order of the information that is revealed, that is secure. So we could take the server isogeny to be much longer than the blinding isogeny, and the message isogeny is sufficiently long so that the composition of this isogeny at the top is much longer than the one at the server one, so that this does require using any sort of SIDH countermeasures. We just use isogeny that are sufficiently long for the attack not to apply. Unfortunately, what we get is something that is secure and slightly moderately compact. It uses much smaller values than much smaller primes than the SIDH countermeasures, but what we get is not an OPRF, because we want that the OPRF, the blinding part of the OPRF, is fully blinding even when the message page is very limited, even when there are only 2 messages. In that case, that means that the server, a malicious server, can sort of guess this curve here, which then would allow it to apply the attacks. So such a construction might work for specific applications of an OPRF, but it doesn't work for a generic OPRF. So we had to turn our attention to the SIDH countermeasures. And we mostly know 3 ways to prevent the attack. One, again, is to use longer isogenies, but that only works for one party, so it cannot protect both of them. The other approach was mask degree isogeny, where we use isogenies of varying degrees, as proposed by Tomoki Moriya. And while this works and is secure in the SIDH setting, its main issue is that it's very hard to build zero-knowledge proofs. In all the proofs that we know to prove knowledge of an isogeny, we create an SIDH square, and then we reveal a parallel isogeny. When we do that, that invariably leaks the degree of the isogeny. So in this case, if the degree is the secret, it's hard to build proofs. So then the only option that seemed to be working is using masked torsion points. In this case, only the torsion points are masked, but the degree is fixed, which is more likely to lead to a zero-knowledge proof. And indeed, we see that it's correct and it works. It does significantly require a much larger prime than regular SIDH, the one that was broken. And it also needs a new proof of isogeny knowledge that needs to be adapted, but is somewhat more likely. And indeed, in this work, we propose a new proof of isogeny knowledge that works with mask torsion. So in the general setting, we have that there is a secret isogeny phi with 2 points P0, Q0, and P1, Q1. And we want to prove knowledge of the isogeny phi together with the fact that these are the images of this. But in this setting, when we work with mask torsion, we actually don't have that, but we have that the points P1 and Q1 are masked by a scalar A. And not only they're masked by a scalar, but we also want to prove that they are masked by the same scalar. So the idea to construct such a proof is, once again, we build an SIDH square, and we use ternary challenges, one corresponding for at each side of the square, so that it means that the soundness error is about 2/3, which we need to repeat this several times. But this is similar to many other proofs of isogeny knowledge. Then, to guarantee the correctness of the points, the images, what we do is that we map the points P0, Q0 across the 3 edges. In order to do so, we do require a significantly larger prime because we want that the degree of these isogenies is co-prime with both the degree of the isogeny that we're proving knowledge of and the order of the points. But if we accept that, we can get a proof that works with mask torsion. The idea then is to somewhat put in input the randomness, the masking value A, is that we split this value over 3 shares that are randomly independent, such that their product amounts to A. And then we masked these first points here with A1, and we masked these points down here with A2. In this way, we have that revealing each edge doesn't really leak any information because the A1 and A2 are uniformly independent of A, but we get that if you map the points P0, Q0 through these 3 isogenies, we get something that is compatible with the top isogeny. The 4 isogeny form a commutative diagram, in other words. And of course, we also need to reveal the blinding values A1, A2, and A3 at each step to make sure that the verifier can check the correctness of this construction. But when we do this, we obtain a proof that works with mask torsion and can then be plugged into the protocol to obtain a OPRF that is resistant against the SIDH attacks. Lastly, we look at verifiability. Verifiability is the property that guarantees that the server behaved honestly and used a key that was the previously committed one. In the construction by Boneh, Kogan, and Wu, they relied on 3 proofs. A proof of isogeny knowledge of the server isogeny, another proof of isogeny knowledge on the server commitment, and then a proof that the 2 are parallel. This third proof, however, is highly interactive. It's based on SIDH, so that the 2 parties basically engage in an SIDH exchange, but then to prevent the adaptive attacks, there is several rounds where one commits and then reveals their secret in a sort of Fujisaki Okamoto transform kind of way. And this leads to a very highly interactive proof. As you can see here, it's 5 rounds, which bumps the number of rounds for the entire protocol up to 6. And this is, of course, not ideal. So what we propose to do is that we sort of ignore that proof altogether. And when we run the 2 proofs of isogeny knowledge for the commitment isogeny and the secret isogeny, we do them in parallel with some shared randomness in such a way that when we need to reveal the bottom isogenies here, the 2 bottom isogenies are parallel to each other precisely when the top 2 are parallel. In this way, we get a proof that is non-interactive because both of these are non-interactive, so we can just apply Fiat-Shamir and get something that is fully non-interactive, so it doesn't require any additional round of communication, unlike the original proof. And it also reduces computations because these are 2 proofs that we already need to be running for the protocol to be secure. And basically, just by using the shared randomness, this guarantees that we sort of can obtain a third proof for free. So this also allows us to obtain verifiability without increasing the number of interactions. So to sum up, putting everything that we've seen together, we propose a countermeasure against the pseudorandomness that doesn't require any special prime, and it's actually more efficient than the original construction. We show how to integrate the SIDH countermeasures and which one were better, and which unfortunately would require a prime of size about 6,000 bits, which is certainly not small and more than 10 times longer than the original SIDH construction. We also provided a new proof that proves correctness of torsion points, but and works with the mask countermeasure. But unfortunately, as I mentioned before, we need a third component for the isogeny used in the proof. So in the end, we end up needing a prime that is 9,000 bit. This is certainly not ideal, but it seems like the best we can do so far. If there were any sort of new developments in SIDH countermeasures that did not depend on masked degree, it's quite likely that we will be able to include those into the OPRF and obtain a much smaller OPRF. And lastly, we provide a new proof of parallel isogeny that is round optimal, and it's significantly more efficient than the original because we can obtain it nearly for free from the other two existing protocols. So if we compare the results of this work with the 3 existing post-quantum OPRFs, we see that we fare quite a bit better. When we compare to the lattice-based one, we obtain the same characteristics, as in it's verifiable, secure, and round optimal, with using several orders of magnitude less bandwidth and somewhat of a reasonable amount. Compared to the original construction by Boneh, and Wu, we only require a slight increase in bandwidth. Despite using the larger prime, this is because we optimized a lot of the steps so that even if we're using premises like a lot larger, more than 6 times larger, we still get something that is only 30% bigger. And this increase in bandwidth is the cost to obtain something that is secure against 2 categories of attack, both the pseudorandomness attack and the SIDH attacks, and that it is round optimal. And lastly, when we compare it to the seaside construction, ours is significantly larger, but that's because a lot of the bandwidth goes towards verifiability. If we did not include those, we get something that is only 30% larger than their construction, while also being round optimal. So overall, what we get is an OPRF construction that is round optimal, post-quantum secure, and verifiable, and moderately compact. This is probably not practical for most use cases. It might be for some, but not all for sure. And it's definitely not competitive with the Diffie-Hellman-based construction or other classical construction, but it is a step in the right direction. And of course, more work will be needed to try to bridge that gap. Thank you very much.
Thank you very much, Andrea. Great talk. If anyone has any questions, just unmute or write in the chat. And yeah. So I wondered, I mean, I guess that of course, since you use these huge primes, it's gonna the computation is going to be quite heavy, right? But is it like in like minutes or hours, or is it like weeks?
So, well, I mean, of all these post-quantum OPRFs, none of them has been implemented.
No, okay.
So when we're talking about running times, it's all based on estimates.
Yeah.
But on top of that, we also have that none of the SIDH countermeasures have been implemented, as far as I know. So even then, we're going off estimates. So with these 2 big caveats, I would imagine that this OPRF requires a few minutes to run. It wouldn't be, it's definitely like less than an hour.
That's pretty nice. Sorry. No, I was just go ahead. Like,
yeah, no, I'm just saying. I mean, the main cost comes from running basically 3 proofs of isogeny knowledge, which corresponds to computing something like maybe like 3,000 isogenies, and each of degree 3,000, which is certainly not efficient. It's a high number, but I think we're clearly in the range of a few minutes. Yeah.
Oh, that's very good. And also, like, then you can kind of argue that it's more efficient than the lattice-based construction, since, you know, sending 128 gigabytes of data is going to take more than a few minutes.
Yeah. I think in that sense, it's because OPRFs like do require this sort of long-term static key, and for some reason, it seems like isogenies are better equipped with working with that kind of long-term constructions compared to like lattices or other post-quantum families. So I do think that OPRFs are interesting objects for isogenies, because it's possibly one of the protocols where like we can actually hope that isogeny-based constructions might outperform any other type of constructions.
Yeah. Yeah, that's a good point. I see there's also a question in the chat by Bruno. So he asks, is your OPRF countermeasure, no, sorry, in your OPRF countermeasure, does the torsion point images that you need to compute after the first isogeny computation need to be obtained deterministically, or can they be chosen randomly? Did you get that?
After, let me go back. Yeah, this is where all the animations come. I'm not sure what torsion points you're referring. If you're referring to the one that you're revealing here as images, or the one that you down here. So the ones that up here, these are just the images of some points that are chosen as parameters on E0. So they, well, they don't need to be, oh, sorry, I see at EM1. Oh, I see. They do need to be deterministic in the sense, well, I mean, yes, they do need to be deterministic, because you want to, that in the end, you map the message M onto a curve EM in a deterministic way, because you want that if you sort of repeated this process with the same message, you also always obtain the same isogeny here, so that you always obtain the same OPRF output. So yes, the only way to do that is that the canonical base that you generate here is canonical and deterministic based on the curve EM1. I also see there are other questions. Let's see. It is possible to generate proofs in the mass degree case using MPC in the head techniques. I don't know. It's possible. I mean, I guess like the thing is that you can always generate proofs with more or less generic proving systems. The question is always how efficient that becomes. There was this recent paper that appeared in the ePrint where they showed that proofs of isogeny knowledge that only proved knowledge of an isogeny without torsion points was quite competitive and better using generic Stark techniques rather than using the one that we've been using for a while based on isogenies. But that, for instance, needs to be noted that only concerns the knowledge of the isogeny, but it doesn't say anything about torsion points. If you include torsion points, that proof, I imagine, would become quite a lot more costly, because you will need to use a completely different mechanism. So, I mean, it's true that like it may be possible to do something with mass degree using generic constructions, including MPC in the head, for sure. It just, in the end, it's just a matter of whether that would be secure or not. And I think that's also a similar answer to the question by Youssef about using ski sign. The issue there, the limitation there is also that ski sign only proves knowledge of an isogeny, but it doesn't prove the correctness of the torsion images. So I think like that's the step that it's missing. And I don't, as far as I'm aware, there is no way to use ski sign to prove correctness of torsion points. If there were, then it could be used, yes. Can you hope to build? Maria is asking whether it's possible to ask to build an OPRF from verifiable random functions. let me think. In a verifiable random function, you have oh no, okay, so sorry, you're asking whether it's possible to combine a VRF with a non-verifiable OPRF to obtain a verifiable OPRF. Yes, I think so. I think so. Of course, I mean, everything needs to be sort of like consistent and works together. But I think at a high level, that should be doable. Although I'm not aware personally of any isogeny-based verifiable random function. I don't know if one exists.
Yeah, thanks very much for answering all those questions, and thanks for asking great questions, the audience.
I think that were all of the questions. I'm not sure if there's anybody left with a question, then please unmute, because otherwise I will go to the closing ceremony, so to speak. So thank you again, Andrea, for the great talk. It was very clear and very informative. For the rest, and also for Andrea, in 2 weeks we have our third session. It's with a mystery guest, so tune in to find out who is the mystery guest. But the topic is During for the People. And if you want to hang out a bit to chat a bit more, maybe also about OPRFs, then feel free to do so.
Yeah, I'll also turn off the recording for the more relaxed session. But yeah, thank you, Andrea.